Good morning, everybody. It's me, Bendoumi Amina, Assistant Professor at the University of Sciences and Technologies Houari Boumediene, in Faculty of Mechanical and Processes Engineering, Materials Science Department. In this video, I will explain one of the methods of material mechanical characterization, which is tensile testing. So, what is a tensile testing? Tensile testing, also known as a tension testing. It is a fundamental materials science and engineering test which a sample is subjected to a controlled tension until failure. Now we move to explain the main of this test or the objective of this test, why we use this kind of test. This is one of the most common mechanical testing techniques. It is used to find out how strong a material is and also how much it can be stretched before it breaks. This test method is used to determine yield strength, ultimate tensile strength, ductility, strain hardening characteristics, Young's module, and Poisson ratio. Let's see the tensile specimen preparation. Tensile test specimens are prepared in a variety of ways depending on the specifications and the norm used. Most specimens use either a square or a round standard cross section with two shoulders and a reduced section gauge length in between. The shoulders allow the specimen to be gripped while the gauge length shows the deformation and the failure in the elastic region as it is stretched under load. In this slide, you can find some definitions of properties or test properties like yield strength, modulus of elasticity, stress, strain, and ultimate tensile strength, and also some formula how to calculate a modulus of elasticity, stress, and strain. Let's see the most important part of this presentation. The tensile testing curve, also known as a stress-strain curve, graphically represents the behavior of a material under axial tension. So here is a general description of the curve. The curve represents two stages. First one is the elastic deformation. The stress and strain are proportional and the material behaves elastically. In this region, the material deforms elastically, meaning it returns to its original shape once the load is removed. In this part, we have the Young's modulus. It's calculated from the slope of this linear portion. And we have the yield point where the material begins to exhibit plastic or permanent deformation. And then the second stage is the plastic deformation. Beyond the yield point, the material undergoes a plastic deformation. The stress-strain curve becomes nonlinear as the material flows and deforms plastically. We have the ultimate tensile strength. It's the maximum stress the material can withstand before failure. It is the highest point on the curve. After that, the nicking, as the material continues to deform. A localized reduction in cross-sectional area. And nicking is characteristic of ductile materials. Finally, we have the failure point. The material ultimately fails at the point of fracture. The failure may occur suddenly or with some degree of deformation depending on the material. Total strain and reduction in area. These parameters are often calculated based on the final dimensions of the specimen after fracture, providing information about ductility. So, understanding the stress-strain curve is crucial for assessing a material's behavior under different loading conditions and designing structures with appropriate safety margins. Different materials have unique stress-strain curves, and variations may occur based on factors such as temperature. As conclusion, we can say that the results of tensile tests are used in selecting materials for engineering applications, predicting performance, and ensure the safety and reliability of structures and components. Thanks for your attention. See you in another video.